Hello, my name is Saeed Hatadan. I'm a PhD candidate at University of Maryland, supervised by Professor Matthias Suiker. Today I'm going to talk about our recent SIGGRAPH paper, Inverse Global Illumination using a Neuroradiometric prior. This is a joint work with Gang Lin from University of Maryland and Jan Novak and Fabrice Roussel from NVIDIA. Let's first review forward rendering versus inverse rendering. Typically, given a set of scene parameters such as 3D mesh, camera, light, and materials, using forward rendering, we can generate a realistic image. Inverse rendering, though, is the inversion of this process. We are given an image, and we are asked to recover the scene parameters. Today, we are concerned only with the inverse rendering. As an example, in this room, we aim to find material properties under known 3D mesh and known lighting such that our rendering I matches the target state. To achieve this, we can define a loss function such as L2 between the rendering and the target state, and use gradient-based optimization to find the correct scene parameters. With the help of a differentiable renderer, we can compute the gradients with respect to the scene parameters and optimize them through multiple gradient steps. There are two broad categories of differentiable rendering. One, physically based rendering, which simulates the physical behavior of light, an example of which is the differentiable path tracer in Mitsuba 3. And two, rasterization and neurorendering, which are approximations of the physical behavior. For instance, OpenDR is a differential rasterizer and NERV is a neurorendering method. Today, we are only concerned with the first category. In a physically based renderer, in order to compute a pixel value I sub k, we trace rays from the camera for multiple bounces. To compute the derivatives of the pixel with respect to the scene parameters, we also need to differentiate the path. This requires differentiable path tracing, which is typically a very challenging task because it involves tracing millions of rays and differentiation with respect to potentially millions of scene parameters. And also because achieving a correct solution might require tracing long paths involving multiple bounces. Since this could be very costly, an easier task would be to compute a direct illumination solution. As opposed to the global illumination, the direct illumination solution would involve forming an image using only the first bounce. Although the direct illumination solution is cheaper to compute, but it also leads to darker renderings due to ignoring the interreflection of light in the scene. Due to this approximation, the inverse rendering bakes the missing energy in the scene parameters. In this example, you can see the recovered albedo is clearly too bright because it is trying to compensate for the missing indirect effects by direct illumination model. In this work, we are only concerned about the models that incorporate global illumination. So let's talk about two existing differential rendering algorithms that solve for global illumination. The first is automatic differentiation of path tracing, or ADPT, which is basically naively differentiating a path tracer using generic automatic differentiation, like what you can see in Mitsuba 3. AD is very simple to implement because you can just throw your code at it and it computes the derivatives for you. Internally, AD keeps a graph of all operations, which is then traversed to propagate the gradients of the loss to the scene parameters. This graph's memory usage could be interactable in case building long path is necessary. And /or, in case of a complex scene, the graph can have too many interdependencies between the nodes. Typically, computing and differentiating the path integrals could be very slow in case of long path. That said, path tracing is based on Monte Carlo sampling, which can provide unbiased gradients, and it can also handle glossiness pretty well. The second algorithm is path replay backpropagation, or PRB by Vicini and colleagues. Under the hood, PRB implements a path tracer, but it has a different approach to differentiate the path tracer, which makes it slightly harder to implement. This is because PRB is an adjoint-based method that models differential light transport in a domain-specific adjoint phase. However, it is memory efficient because it involves smaller AD operations instead of keeping a gigantic graph. Since PRB still solves path integrals, it could be slow in case of long path, but it also has unbiased gradients and does well when it comes to high glossiness. As opposed to these, I want to introduce our method where we use a neural network as a radiance cache to provide global illumination. So, in comparison, our method is simple to implement because it just uses vanilla AD, no extra precautions needed. And the memory usage is actually bounded because we trace limited number of bounces, resulting in short path, and as a result, it could be also much faster because, again, our paths are shorter. But the issue is that it will have biased gradients. And we expect that the quality of our method degrades if glossiness goes very high in the scene and there are very complex interreflections as a result of specularity. This table summarizes the pros and cons of these methods that all provide global illumination. Okay, the question is, what is the key difference of our method compared to path integral based methods? As we discussed earlier, in order to form an image that accounts for global illumination, the path integral based methods bounce array multiple times in the scene. Instead, our method uses a radiance cache to replace part of this path. Since this radiance cache provides the incident light at the first intersection, it removes the need to build the rest of the path. Given such a radiance network, the question is how to train it. Our training of the radiance cache is inspired by prior work called neuroradiosity, which is basically a method of finding the solution of the rendering equation using a single neural network. Okay, let's dig deeper in this method by first looking at the rendering equation, which is the foundation of the physically based rendering methods. This equation ensures that energy conservation holds at every scattering event in the scene. In other words, at every scattering event, the outgoing radiance equals emission plus the amount of incident light that is scattered towards the outgoing direction. Actually, this is too complicated to work with. Let's use the operator form, where we replace the integral term with an operator called transport operator, which evaluates the radiance function L at a transported location. Even more simply, by removing the inputs and the parentheses, we get L equals E plus the transport operator. Typically, in forward rendering, the unknown is the term L, and the goal of every physically based renderer is to find the function L. Neuroradiosity suggests parameterizing this L with a neural network. Now, given a randomly initialized set of network parameters, the sides of this equation wouldn't be equal. Neuroradiosity takes the difference of the sides of this equation and calls it a residual. Ideally, this residual should be 0, but it is not because our parameters are wrong. Then we define the loss as the L2 norm of the residual. By minimizing the loss, we can find a set of parameters for the radiance cache such that it satisfies the rendering equation. Let's see what each term means in the residual loss. In order to evaluate the first term, L theta at an arbitrary location x and direction omega, we just need to query the radiance cache directly at that location and towards that direction. Here we show the outgoing radiance resulting from a query to the network using a green arrow. The second term is basically emission plus the transported radiance, which involves querying the network at the subsequent bounce, shown as a green arrow. Then the result of the network query is treated as the incident radiance at location x and scattered towards direction omega. In a few words, the goal of the residual loss in neuroradiosity is to make sure that at a given location and direction, the predicted radiance is equal to the transported radiance. Or in other words, if we use the original terminology of neuroradiosity, the left-hand side LHS should be equal to the right-hand side RHS. To make things even simpler, we substitute the LHS and RHS in the residual loss. LHS and RHS refer to the sides of the rendering equation, and minimizing the residual loss will ensure these two sides are equal. Let's jump back to our method now. Now that we know what this residual term is, let's not forget our original goal, that is, to create renderings using this radiance cache, compare them to the ground truth, and optimize scene parameters. So the question is now, how to render an image using this radiance cache? Well, it's simple. In order to render a right-hand side image, we shoot the rays from the pixels and evaluate the transported radiance, which involves querying the radiance cache at the subsequent bounce. Now that we have our right-hand side rendering, we can actually compare it to the ground truth and compute a photometric loss. Since the right-hand side term depends on the scene parameters, we can just simply use automatic differentiation and compute the gradients at the first bounce. Thanks to the fact that the required graph of operations is limited to one bounce, the memory usage is bounded. There we go. Here we see the essence of our method. In addition to the photometric loss, we add up the residual term as a radiometric prior that imposes a physical constraint on the radiance cache. And we train the radiance cache and the scene parameters simultaneously end to end. Let's go over some results and experiments now. We conduct inverse rendering under known mesh geometry and lighting and use separate neural networks to represent the spatially varying BRDF parameters, albedo and roughness. Our experiments are on a RTX 3090. Our implementation is on Mitsuba 3, and because we use neural networks to represent albedo and roughness, we have to turn the megakernel feature off. Here, we present an equal time reconstruction comparison of our method to the baselines. Our results converge to the right solution much faster than the path interval-based methods. And now albedo, and now the roughness maps. Please note the average path length in the staircase scene is 4.7. We also illustrate the iteration time per step here that shows our method is significantly faster. In a different experiment, we study how time and memory usage in our method scales compared to the baselines. We designed a closed room with diffuse walls, and there is a single area light on the ceiling. By varying the albedo from 0.3 to 0.9, the global illumination effects become more significant, and a longer path length is necessary to account for all interreflections. We report the peak memory usage and time per step against albedo. As expected, AD's memory usage increases as the path length increases, but PRB and our method are agnostic to the path lengths. In terms of time, PRB and AD are path integral based, therefore becoming slower as the path length increases, but our method's performance does not depend on the number of bounces. In this section, we go over the additional steps to further improve the radiance cache quality. So far, we have only used the radiometric prior to train the radiance cache. In this prior, the left-hand side and right-hand side terms are sampled at the first intersection, which we call one bounce prior. Although in many cases this is enough, our method is not limited to the first bounce prior. In fact, one could use extra bounces to sample the residual at new locations that are not directly visible by the camera rays. Please note that at this extra bounce, we do not update scene parameters using AD, and we solely use it to find extra samples for the radiometric term. As an example, in this hot dog plate, between the buns, the recovered albedo maps has artifacts, which is fixed when we compute the prior at 2 bounces. Another improvement to the radiance cache can come from the ground truth images. Instead of only relying on the radiance cache term, we can additionally fit the radiance cache to the radiance stored in the ground truth pixels directly. For this purpose, we render a left-hand side image at the primary intersection and compare the resulting image to the ground truth. We empirically witnessed marginal improvements to the radiance cache. Another question is, what if we only rely on the ground truth images and completely get rid of the radiometric prior? Here, we compare the results for albedo recovered from our method with and without the residual. As you can see, the holes in the Lego exhibit artifacts in case we remove the residual. This is because the prior trains the radiance cache at additional spatio-directional locations. Lastly, I would like to talk about bias in the gradients resulting from our approach. Basically, there are 2 sources of bias in our gradients. One is that we ignore the secondary gradients, meaning that we only update scene parameters at the first bounce, not at the later bounces. One way to mitigate this is to delay querying the radiance cache to a further bounce. In other words, during rendering, we would need to trace more differentiable bounces before we query the radiance cache. And the second source of bias is the approximation nature of neural networks. For an extensive study of bias, we refer to our technical paper. To conclude, in this work, we proposed a novel inverse rendering method using a radiance cache that accounts for global illumination based on a radiometric prior. In comparison to path integral-based methods, our method achieves significant speedups despite being simple to implement due to using automatic differentiation. Despite using vanilla AD, our method uses bounded memory. However, our gradients are biased, and it is presumed that the quality of our method degrades with high specularity. Thank you for your time.